Dr. Maegen Rochner is a geographer and tree ring scientist teaching and conducting research as an assistant professor of geographic and environmental sciences at the University of Louisville. Her research focuses on the use of tree ring data to reconstruct past climate and environmental conditions. This has included investigating over 1,200 years of climate and environmental change in the Greater Yellowstone, reconstructing landslide activity in Great Smoky Mountains National Park, and analyzing historical fire and slash pine ecosystems in the Florida Keys. Her recent research has focused on local applications of tree ring methods in Kentucky, including projects focused on urban forests and their responses to climate change and urban heat islands, and the tree ring dating of local historic resources such as cabins, buildings, and artifacts. Her work in Louisville and the surrounding region continues to foster collaboration with specialists from other Kentucky universities as well as with local officials and community organizations. And she hopes to inspire love and support for Kentucky's natural forest. Please give a warm welcome to Dr. Maegen Rochner.
Great. Hello, everybody. Thank you for coming. I'm so excited to see so many faces here to learn about tree rings. And thank you again to the library for inviting me to be part of this short course series. I always love to have the opportunity to speak about something that I am very passionate about to others. And that thing for me is tree rings and trees in the environment. And as you'll soon know, pretty much everything outside, but we'll get there. Today, we're going to sort of start the course off with a basic introduction on what is tree ring science. And the goal is to, as we progress through the series, to introduce you to different applications, the tools of the trade, and specifically sort of how we use tree rings to understand the past, and then how we use tree rings to understand the future, or what could happen to these things that we love in the future that we face. So I wanted to start with a little bit about me. So I'm Dr. Maegen Rochner from the University of Louisville. I teach in geographic and environmental sciences. I was looking for a picture that I thought sort of captured who I was. And while digging through some old albums on Facebook, because we don't usually keep our phones long enough to keep our pictures on those, I found this picture that a friend had taken of me while we were adventuring in Vermont and New Hampshire. And I thought, well, yeah, that's pretty much it. That's where you find me, how you find me all the time, that I'm outside, looking at something, inspecting something. Often it's rocks and trees. So in this case, I'm sort of straddling the creek, looking at all of the rocks and trying to find the really cool ones. My undergrad was actually in geology and English. It took me a little while to figure it out, so I double majored. And my graduate degrees are in geography. But I really find myself, and why I think I found myself at home in geography is just I have this innate curiosity about everything. And geography, anyone in the room, geography is the study of land, our natural world. It's the study of things that occur over space. Geographers study things spatially. Well, everything occurs over space, right? So geographers literally study just about everything. And I thought, what a perfect place for me, because I am interested in everything, but particularly in things in the natural world. So I ended up as a geographer. And tree ring science is specifically a tool or a toolkit or a method that I use to investigate a lot of different environmental questions, but also human questions and human environment, because we know that those things are very closely intertwined. I also like to start with a quote that I stumbled across relatively recently. Who has read Robin Wall Kimmerer's Braiding Sweetgrass? So being in a library, that's a big plug. Everyone should read that book. Everyone should read that book. I highly, highly recommend it. And a few folks in Kentucky, we were lucky enough to actually meet Robin at the University of Kentucky, and she came to give a special talk and sort of a meet and greet and answer questions in the audience. And she's one of my heroes. Even more so when I stumbled across this quote and thought, there is no more perfect way to explain tree rings and what I do as a tree ring scientist. Robin Wall Kimmerer is a botanist and studies plants. I'm a tree ring scientist, and I study specifically trees and their growth patterns over time. So in her book, Robin says, "To me, an experiment is a kind of conversation with plants. I have a question for them, but since we don't speak the same language, I can't ask them directly, and they won't answer verbally. But plants can be eloquent in their physical responses and behaviors. Plants answer questions by the way they live, by their responses to change. You just need to learn how to ask." I use tree rings to ask the trees about their life history, about their responses to change, whether that be climate, disturbance, humans. So learning about tree rings is partly learning how to speak one of the many languages of trees. In my case, looking at their responses. So we're here today in part one to talk about what is tree ring science. You're going to hear me use these terms interchangeably. Tree ring science is kind of the more approachable one. We know what tree rings are. Dendrochronology is the more official, scientific of them. But they both mean the same thing, and I'll talk specifically about what this term means here shortly. So I wanted to ask you all first, how many in here, raise of hands, have heard of tree rings before? Keep your hand up if you've looked at tree rings before, right? Almost everyone, when you're a kid, you notice tree rings or you learn at least the basics about them. So what can we tell by looking at tree rings? Any volunteers? Yeah, over here. Yep, the age. What else? Anything? Yeah, if it was wet or dry, the climate conditions that tree experienced. Anything else? Yeah, the health of the tree. Is it doing good? Is it doing bad? Why? What's driving that change? Any other? Yeah, up here.
If there was a fire.
Yes, if there was a fire or another disturbance, there was something in the middle.
The age of the tree.
Yeah, so how old they are, what's impacted them. In terms of climate, environment, disturbance, people, all of those things affect the ring of the tree. Sometimes it affects the width, sometimes it leaves this very distinct marker behind in the ring that tells us about that disturbance that happened. So if you've looked at tree rings, anyone counted them before to see how old a tree was? I'm walking in the neighborhood and there's a new tree cut down, which is sad, but I'm like, every time there's a tree out in the woods and I can see the rings, I'm like, how old is this? What was its life like? I look for scars, I look for cool things, because I'm just always observant. I also notice tree rings in built environments. I'm the friend at the bar who's like looking at the ends of the live edge top. And I work with historic timbers and buildings and things too, so I'm also thinking a lot about the history that can sometimes just be hidden right underneath of your feet in things that we've built and trees that we've cut down. My partner gave me a piece, so he does a little bit of woodworking, that he got off of a pallet and made a coaster. And it was oak, and just in the size of a coaster was over 150 rings. 150 years of life captured in a few inches, and now it's a coaster for us to sit our drinks on, right? Very both cool and maybe a little sad at the same time, but it puts it into perspective just how much life trees experience. So tree ring science is also known as dendrochronology, dendro for tree, and chrono for time. I specifically, as a dendrochronologist, study the rings of a tree. Dendrology is very similar, but different specifically from what I do. I'm looking at the growth of trees and how it changes over time and evidence of different things that have happened to that tree. Specifically, it's defined as the science or technique of dating events, environmental change, even archaeological artifacts. And I'm going to talk more about that in a future session specifically, because there's a lot of archaeology to be done here in Kentucky. By using the characteristic patterns of annual growth rings in timber and tree trunks. So we use the pattern of growth in trees to investigate past environmental change. So just to summarize, tree ring scientists use patterns in tree growth to understand past environmental conditions. So I want to pose a few scenarios to you all. So this tree is an example of a tree that's had relatively good growing conditions, and I'll tell you that the space between each black line is a ring. It's 1 year. So this tree, pretty fast growing, pretty consistently growing over time. So it had good growing conditions for its whole life. What sorts of conditions would you expect would allow a tree to grow well? Yes?
Plenty of water, plenty of light, photosynthesis.
Mm-hmm. Yeah, water, light in the back. Yeah, air quality could play a role. I saw this first.
Nutrients in the soil.
Yes, nutrients.
Being planted in the right place.
Being planted in an appropriate place, and that can vary by tree. Trees can do better in different environmental conditions depending on the species. So some trees actually might like it a little cold and dry. Some trees might like it better warm and humid. So it can vary by species. But in general, when we think about trees growing well, and when we think about that in Kentucky, water, light, warmth, nutrients, a good growing season, and that doesn't get interrupted, air quality, pollution, things like that could affect the growth of a tree. So this tree was growing pretty well. This is actually the tree we avoid in dendrochronology, and we'll get to why that is. There isn't much of a story here to tell other than this tree was very happy. It got everything it needed. So let's do another example. So you can see more variability now. So this tree did not have good growing conditions its whole life. It maybe started out a little slow, and then something happened that allowed it to grow quicker. This ring's pretty narrow. Something happened at that time. It slowed down a little bit, maybe sped up a little bit towards the end, but there's variability. It speeds up, it slows down. There's a narrow ring. So what sorts of conditions might reduce the growth of a tree? Drought, fire, some sort of that injured the tree or hurt it in some way.
Hurricanes or tornadoes.
Yes, hurricanes, tornadoes. If they don't kill the tree, they can take out a lot of the limbs, and it'll slow down its growth. Human interference for sure. Yeah, an illness or disease or a fungus or something that's gotten in and infected it. Some insects maybe. Yeah, so competition, having to fight for sunlight. Some species are more shade tolerant and can do relatively well under the canopy. Others are not. They're more intolerant. But as they're fighting for dominance in the canopy, you can see that affect their growth rates over time. So changes in climate extremes like drought, disturbances like fire, human interference. It always saddens me in my neighborhood when the power company, for example, comes in and clears out part of a tree for power lines. I understand why they have to do it, but often it's fairly aggressive and just to get out of the way of the power lines, right? Not thinking as much about the tree. Now you can call your friendly neighborhood arborist and maybe get ahead of the game and do a more healthy pruning of your tree to keep it out of your power lines. The power company usually doesn't do that. They might. I don't want to call them out too much. But we've seen it. And so it can hurt the tree. You know, you take out a big chunk of the tree's canopy, it's going to show up in that tree's growth. So this tree grew unevenly. Yes, do you have a question? The question was, what if you have a young tree and you have kids who like to climb it? I climbed trees, and through that process grew very close to them. I think relatively speaking, they cause minimal harm to a tree. Now, if you knock out a bunch of limbs or you knock out a big tree branch or something, but the tree's gonna be fairly resilient to the minimal disturbance that climbers might cause. Yeah. Mm-hmm.
Outside of the narrow and close lines, what can happen until that it has growth?
Well, we'll look at instances of damage, indication of trauma or disease or damage. It's usually the change in growth that tells you. Sometimes more direct things, like for fire, for example, leaves a scar. There's an insect that leaves obvious evidence of being there, but also leaves behind a fungus that stains the wood blue, and then you can tell that that has impacted the tree. So sometimes there are other lines of evidence that can add to that.
So the lines do not, they're not spaced out evenly. That's the side of the tree not growing. I guess. In good condition.
Yes, or in favorable conditions. So sometimes, good is kind of maybe a human word, but in different species respond differently to different conditions. But it experienced conditions that were not favorable to its growth if the ring is narrower. So maybe it was drier that year, maybe it was hotter, maybe the growing season was cut short. And then we try to work out what actually caused that.
So is it right to assume then the first picture you showed us had beautiful, nice concentric circles, evenly spaced pretty much through.
Mm-hmm.
So that is an indicator of a tree that's doing well. So all these other pictures that you've showed us so far where they're not concentric and they're not in the same shape as the first one, you can tell by that the tree has been exposed to unfavorable conditions.
Yes, so the question was about complacency. It's called complacency. It's what we call it when the tree grows quickly and equally each year. There's not much pattern or variability. The tree's growing in relatively favorable conditions. It's getting what it needs to grow well and to grow consistently. Also, the environment around it is probably not changing very much year to year. It's fairly consistent environmental conditions as well. Where if there's more variability, there are at least times when that tree's experiencing unfavorable conditions, right? Now, and I could be careful saying the tree's doing good versus not good, because it's relative. And just because a tree experiences maybe a drought in one year, they're pretty resilient, and we can see that a lot as well. Conditions return to favorable, and the tree returns back to relatively normal growth. Any other questions? You reminded me that I meant to say, please raise your hand. Don't be afraid to interrupt me to ask questions as we go. It's more like a class than a lecture, right? So I want you all to interact with me as well. So if you think of something, please ask.
I've always wondered where the tree rings show that all tree species slow growth over their age. Is that true?
So what's happening, the question was about, do all tree species slow growth as they age? Now, before I became a tree ring scientist, I thought about trees like humans. We grow really fast when we're little, and we get bigger and bigger, and then we reach sort of max size. And maybe we get smaller again later. But, it's like trees are like humans. We grow really fast in the beginning, and then we even out over time. That's not exactly what's happening. So there is this natural growth curve in a lot of trees. Now, if they're experiencing more complex environmental conditions, it might not show up as clearly, where they start growing really fast, and then they slow down over time. So I always think of trees are like a line graph. They slow down and sort of even out over time. The rings are getting smaller. The reason, though, that that's happening is imagine a tree that's this tall and very, very tiny. The same amount of wood on that tree can make a really big ring. But once the tree gets this big, 50 feet tall, the same amount of wood would make a much narrower ring. So that wood's being distributed over a much larger surface and area. So just naturally, the rings get narrower. Right? Now, the canopy gets bigger and the tree can produce more hormones to increase more growth over time too as it gets bigger. But that's the reason we see that trend. Now, part of it too is often, say around here in Kentucky, we have a pretty good history of agriculture and logging that took almost all of our old growth out of the state. And a lot of the parks around Louisville, the parklands, Bernheim in some areas, are trees that have established in open conditions, sort of reforested, previously farmland. Those trees, when they started growing, had little to no competition, just growing out in the open. They would grow really fast. But as they grow, all their neighbors start to get bigger and bigger too, and the canopy starts to close in, competition starts to increase. So you also have in that sort of environmental condition, where they start in the open and get older and closed canopy, you get that sort of change in growth as well. So you see that in a lot, if you look at your lumber, which I do, again, like look at tree rings and everything. If you look at your lumber, you probably see that real big fat rings in the beginning that get maybe smaller over time. So a lot of our timber is plantation grown. A lot of the pines are sort of planted in rows in open conditions. They start growing really fast, and then all their neighbors get older and they get shaded in a little bit, and then it gets cut down and repeated. But you're seeing that growth pattern as well. Yeah.
Is there a record in Kentucky of how old is the oldest trees and what area do you find them?
Yes, so there are records of, well, across the U.S., there's usually the oldest tree in each state. The question is about, are the records of the oldest trees in Kentucky? Sometimes they might tell you what park you'll find them in or area, but not specifically where they are, for a good reason. They want to protect them. For example, anyone know of Floorcliff Nature Sanctuary near Lexington? They found chinkapin oaks that date back over 400 years. So here's a question for you. If you were trying to pick out an old tree, what would you do? What would you look for? Big? Tall? Big trunk, tall, right? The bigger, the better. That's usually actually not the case, right? Yes. So there are lots of examples, and I actually brought some cores to show, like, this is a 600-year-old tree out west and a 100-year-old tree in Kentucky, right? The conditions matter, and it's not always the bigger is the oldest. You can never really know without coring. That's the disclaimer. But a lot of big trees, say when you walk around Louisville, in my neighborhood, there are huge red oak trees. Huge. But they got to be huge because they started growing with no competitors. They were in someone's yard, fertilized, watered, taken care of. So they grew really quickly and really fat. Really happy trees. You core them and the rings are like bigger than your thumb. I've seen like 2-inch thick rings. Really happy trees. Versus, imagine maybe you're a tree that started under the canopy, you've already started in closed canopy conditions. And you've had to fight your whole life. And usually I say when you look for old trees, don't look for the big ones, look for the ones that have been through it. Like if it looks like it's been through it, it has. It's had to fight to survive. So they're twisted and they're gnarly and they're like growing like this. They have sparse canopies. They often have big branches higher up, not lower down. I found trees in Cherokee Park that are 400 years old. I also don't tell where they are. They're chinkapin oaks, seems to be a trend in Kentucky. They're huggable. So I say huggable trees are the ones I can wrap my arms around. 400-year-old trees in Cherokee that are huggable. They had a hard life. They were there before like most of the history of this area, at least in terms of settler, colonizer history here. They were there before it became a park. Somehow they persisted. And now they're just surviving, sort of hidden away. In Cherokee, there are also these gigantic poplars that are not even half that old, that are just massive. So size is not always a good indicator. Yes? Yes, you can never really tell for sure without coring it, but there are indications. Big branches higher up, a sparse crown. So I always say if it's big and it's straight and its crown's like wide open, it's not an old tree. It's a happy tree, right? If it's gnarly and twisted and it's got a sparse crown, it's got big branches higher up, that's the older tree. That's the one you're looking for. Yeah.
There's a tree at the zoo.
Mm-hmm.
That's an old oak tree that sprouted in like 1800, and the way you described that with the gnarly and the branches at the top that don't have a lot of leaves or canopy looks just like what you just described.
Yes, and actually I'll be coring that tree. Yeah, I'll be coring the tree at Louisville Zoo to find out for sure how old it is. No. So, I mean, technically, yeah, you're doing like a little injury to the tree. You're not doing really much more harm than a lot of birds and regular insects do. I've heard it explained in terms of living tissue, you're taking about a fingernail's worth of living tissue away from that tree. And the tree will usually plug it with sap or resin really quickly. You go there a year later, you can find your hole maybe still, but it's all plugged up. The tree will do that to keep anything from getting in. What you do need to be careful of, for example, I worked with a species out west that was being attacked by an invasive fungus, and you don't want to spread the fungus with your tool. So we would have to use fungicide on our equipment. So we weren't responsible for infecting a tree with something. So you do have to keep that in mind. Yes. So the question is about utility companies and their timbers, probably plantation-grown timbers. So places where the goal is just produce as much wood as possible as quickly as possible. And if you look at some of the tree rings on those, they're really, really big, fat tree rings, so they're being planted in open conditions in rows and grown very quickly to produce, especially those straight, really straight poles. The question is, how long does it take for a tree to get big and tall? It depends on the species. So certain species grow faster than others. Again, you further it along by like letting it establish in the open so it shoots up real straight and real fast. And sometimes you're talking like 15, 20, 30 years. So if only a few decades to get that tall. Whereas if you look at some, areas where they're not being grown for that specific purpose, it could take 80, 100, 120 years for it to get to that certain height.
Why is there that darkness? So clearly it grew to a point and it's darkness. What causes that darkness?
All right, so the question was, what causes the darkness in the rings? We're going to talk about that. Yeah. Yeah, I have like pictures, right? Like I can show some examples of some of these things. So it's called early wood, late wood. So it's just different season wood within the course of a year. And as the tree goes into dormancy, the wood gets more dense, the cell walls get thicker, the cell lumen area gets smaller, and so that shows up as a darker band in the ring over time, especially in conifers. So thinking about what affects trees, this one's grew unevenly. The same amount of rings are over here, from here to here, as there are from here to here. They're really narrow on one side, really wide on the other. What do you think might cause a tree to grow unevenly?
Is that just sunlight being uneven on the tree? So half in darkness, half in light?
Yeah, so it could have to do with the tree trying to compete and find its way to sunlight. If you've planted a tree in your yard, which I have a service berry, I might need to help out because it's like doing this, right? It's going for the light, right? What else might cause a tree to grow unevenly? Yeah. Yeah, so maybe human interference, construction, winds, yeah. So in certain areas, you see trees that are they're called crumholds, especially in high elevations. They even grow along the ground. So crumholds trees are like growing along the ground because there's such consistent and strong wind in one direction over time. Even if it's not that extreme, yeah, the wind can affect the tree. Sometimes you see twisting in trees because of wind. So you're a good direction. What is pushing on a tree? So what else might sort of push on a tree?
Growing on a hillside.
Yes. Yes, so growing on a hillside, trees, look at the hillsides around here, and you see sort of trees that are doing this. They're uprighting themselves to go straight. They do what's called reaction wood to upright themselves because of that. Yes. Oh, yeah. Yeah, so snow loading. I actually have some little bitty babies from Lake Tahoe. I was just there last week. And they have the reaction wood in them from snow loading. So the little bitty trees, in every winter, they get buried by a bunch of snow. It pushes them over, and then they try to get upright, and then they get pushed over, and they try to get upright until they can finally break through. It is good exercise, right? They have to fight to survive. So this tree was probably pushed.
How about a tree that grew right beside it, and then it died? But that mark still shows the
So, yeah, the potential answer was a tree growing beside it that died. Now, usually what would happen there is you might see this unevenness because trees are competing, a little bit, and it's like trying to get light. But usually what happens when competition is removed is that you start to see an increase in growth all around the tree. So you'll see this, what we call a release in growth. It just suddenly starts growing much faster. And usually one cause of that is removal of competition. So it has access to more water and more sun and more of the nutrients, so it can grow faster. Yes? Yeah, so this is idealized a little bit. If you look at some trees around here, you can see a lot of really irregular growth for a variety of reasons. Growing around roots or over scars, or where two trees have merged together over time. They're very rarely these perfect little concentric things. But it's still a reflection of what that tree's life was like, what it had to deal with. And I personify trees a little because I think about them in that way. But I don't want to force those sort of human ideals on a tree, but it helps me explain what they're experiencing. And then lastly, injuries. So what sorts of things, we've kind of already covered it, what sorts of things would leave behind an injury in a tree? Weather. Yeah, what could the weather do that would harm a tree? Fire, yeah, fire scar. Lightning. Yep, flood damage. Snow and ice, knocking out part of the crown or some of the limbs. Yeah. Yes. People carving their initials into it. Beavers. I had a colleague who studied moose herbivory because they would eat one species in the winter. They would eat the phloem under the bark. And you could actually, if it left a scar behind you, sort of look at how increased moose herbivory. Looking at trees. Yeah.
I've seen trees that have old signs that kind of grown into them.
Yeah.
I don't know if it's
Yes. Yeah. Barbed wire, metal signs, bullets, all sorts of stuff around here you find in trees. It will grow over it, and you might see irregular growth and sort of callus tissue around that object, and sometimes leaching. When I core into a tree that has barbed wire in it, I get a lot of blue and purple, like staining from things that are leaching out of the metal in the back. Yeah. Yes. Insects are one. Yes. So, usually not enough long-term harm. Now, if you see like the sapsucker and others that just like bore holes all over the surface of the tree, that's probably doing some harm. And you can actually kill a tree. The living tissue of a tree is just underneath of the bark. All of it becomes transport mechanisms and structures, but the part that's actively living, growing is just under the bark. You can kill a tree by what's called girdling a tree. Foresters do it sometimes to kill certain species or to daylight others, and they just go with a chainsaw and cut a rim around the outside. They don't cut it down, they just cut a rim around the outside. They're cutting through, just like if you wrap something around your arm and left it there too long, you might lose your arm. If you wrap something around a tree or you cut off that circulation, you will kill the tree. So you see this sometimes happen around here with fences and fence wire and things as they get wrapped around. If you're like me, shame on me as a tree ring scientist, you propped up your maple tree with the rope against something and forgot to check it periodically. I didn't think about it growing as quickly as it did was the problem. I came out and it had started to grow over the rope. And if I'd let it go much longer, it could have killed the tree because it would have cut off its circulation. So if insects or woodpeckers or anything did happen too, or if I came out and bored a tree all the way around it and I just did it just perfectly to restrict that circulation, you could kill or really hurt that tree's capabilities to grow. It would have to, it has to be usually a decent portion of the roots or the crown that are damaged, or something that takes out a decent portion of the circumference of the living tissue around the tree. But I've seen fire scars on trees that were this big, and it killed 3/4 of the tree. And then it grew all the way back over. And it's like this big now. And you don't know that scar is even there until you core into it. So they're really resilient. Yeah.
I see old trees frequently hollow from the middle out.
Mm-hmm.
Do they ever fill in? There's a tree. Once it dies in the middle, the tree has no way of repairing that.
Right. So a lot of trees rot from the inside. Now, and they don't have a way to fill that back in. Now, because the living part's the outside, it can go on living for a long time. What it loses is structure. And also, things that get introduced with rot. Other fungi and insects that can also cause damage over time. But often it's to structure, and the tree just ends up failing eventually with that damage. You can see trees out west, you can see trees, there's only like 4-5 inches strip living up just one side out to one little branch. That tree's technically still alive, but the rest of it's all just structure, just staying there, not actively growing anymore.
What overall effect is all the wildfires in the West and all that going to ultimately have for all the trees out there? Can they recover from those fires?
So my hope is to talk about wildfire in more depth in a future class to sort of abbreviate a little bit. A lot of trees are fire adapted, even fire dependent. There are trees that they have what are called serotinous cones. that only open in the presence of fire. And it's adapted in such a way. So it's a species that likes to establish on bare mineral soil in open conditions. What you get right after a fire. All the leaf litter's gone, you're just straight on the soil, lots of sunlight. And because of that, the tree has serotinous cones that will only spread seeds after a fire. So the seeds get spread when there's bare mineral soil and lots of sunlight. It's set up just right. So the tree only propagates in the presence of fire. Those are fire-dependent species. Humans have removed fire from the landscape in many cases, and as I will go into hopefully later, setting ourselves up actually for worse conditions. But because of that, we've either suppressed fire or excluded it, things like laws that actually restricted indigenous cultural burning on the landscape and using fire as a tool. Fire has been removed from the landscape, and so those species that are fire dependent are declining. An example a little bit closer to home is the Table Mountain pine. Maybe a little in Appalachia at the highest elevations, but a lot in Great Smoky Mountains National Park. After the most recent fire, Gatlinburg fire, you see baby Table Mountain pines everywhere. Like they were just waiting for that fire. Even though you went up there and the whole area would look devastated to us, the Table Mountain pine was like, finally, it's my time to shine. I can outcompete all the other things that had choked me out for so long. We see around here that actually oak prefers fire, not because it's fire dependent like Table Mountain pine, but because it prefers sort of more open grown conditions, drier conditions, versus maple, for example, that will do better in the shade in wetter, more humid conditions. So we see this sort of flip-flop happening a little bit around here, even from the removal of fire. We don't think about fire much around here in Kentucky, but it did play a role in our forest as well. So those forests can come back. And we might have to talk about why we see more of these what are called high-severity crown forest destroying fires that we see now that might have existed naturally in the past. So I guess long story, a little short, some trees do well actually in the presence of these fires, some do not. But we do see forest change as a result, usually of that type of fire moving through. Serotinous. Put me on the spot. I'm not a good speller on the spot. It's like I could write it down, but I can't speak into a microphone. Was there a question in the back? Yeah.
Probably know the story of a Kentucky tree called the living staircase.
I actually don't know.
Well, the living staircase is in Pine Mountain State Park. The tree was at the top of a ridge that was very sharp. So there was nothing but air on the side of it.
Mm-hmm.
It was felled either by someone, a storm knocking it over, or someone started to cut it down. But the tree lived for almost 100 years after that happened, with its roots higher than its branch. It fell
Mm-hmm.
down.
Yes. So I'll have to, is it still living today?
Unfortunately, no.
Okay.
Probably during my life.
So I'll have to look into the living staircase tree. Next time you're out in the woods, look at just how resilient trees are. Pushed over, and part of them stays alive. One branch just takes over. I've seen trees that do this, and one branch is like, okay, I'm the tree now. I'll take over from here. You see a tree where this whole main stem is gone or knocked out by wind, lightning. Pretty common in the bluegrass. If you're driving through the bluegrass, a lot of lightning and wind damage. And the other branch over here is like, okay, I'm the new leader now. And so you can see that, like pretty significant damage to a tree, but it just keeps on keeping on. So we're kind of ahead of the game a little bit in terms of like explaining what tree rings are and what we can tell from them. So a little bit of a recap. I mean, many of you have looked at tree rings before. So what I do as a tree ring scientist, I don't go around killing trees. I don't cut them down to see their rings. But I am at this, what we call the cross-sectional view. So if you did cut a tree down, that surface you've looked at as a kid, or hopefully now still, to count the rings, that cross-sectional view, that's what I'm after. And I get it using an increment borer. So those who are here next week, we're going to take an increment borer outside and core a tree. So you can see how this works. And actually take a turn at it if you want to. A lot of people might be there, so everyone can just go one little turn, and we'll get into some of those big oak trees. We extract a core that is slicing across that cross-sectional view. In that core, we can see the rings. Now, I've put an example of a conifer up here, and this gets to your question in the back about dark. You have a light band and a dark band. Together, those are 1 year. This is a conifer, keep that in mind. Oaks and maples, they all look very different. This is a conifer. The light band and the dark band equal 1 year. The light band is what we call the early wood, and the dark band is the late wood. The early wood is the earliest wood of the season. It's the start of the growing season into the early summer. Thin cell walls, big luminary, big open cells, transporting a lot of new stuff. The tree starts growing. And as it goes through into late summer towards dormancy, we see the darker band, the late wood. That is where your cell walls are getting thicker, the luminary are getting smaller. When you can see this at a cellular level, you sort of see the cells they look like they're getting smushed, but they're just getting smaller, and their walls are getting thicker, and you see this denser wood as this darker band. It's getting ready for dormancy. It's shutting down. And then it repeats in the next year. We look at the changes in the growth over time. So we look for things like, how are the ring widths related to climate? Is there a relationship between ring width and precipitation, drought, temperature? And that could be max temperature, min temperature. So what sort of climate factor is driving that tree's growth? Maybe there's a suppression, we call it. So there's a sudden change in growth. So it's growing pretty happy right here, and then bam, something happened to that tree. That's like over a 50, 60% growth reduction in 1 year's time. That's pretty quick reduction, and then that reduction is sustained for a few years. So something caused that tree to reduce its growth. Maybe it was insects, maybe it was fire. Insects would come in, and insects are either defoliators, so they hurt the crown, reducing photosynthesis, or they're borers, they're bark beetles, they eat the phloem, the living tissue under the bark, causing damage to the tree and reducing its growth. Maybe we see one narrow year, and this is what I see a lot in Kentucky. So the narrowest rings in trees in Kentucky, so far in my research, have tended to be correlated with drought. The years that show up in our trees are drought. The opposite too, the really big rings, pluvials, really wet years. So they're responding pretty strongly. In between, they're relatively happy, growing relatively consistently, but drought versus really wet years are showing up. Maybe there's a scar. This could be from fire. This is actually an example of a fire scar in Montana. We can actually, for fire and other injuries that leave behind a scar, we can sometimes tell the season of the year. Not just the year, but the season of the year that event occurred. In this example, it was a late wood scar, so it's late in the season, as the tree was going into dormancy. And since then, look how much that tree has healed over. It's curled over. Each year, it tries to seal that wound back up. Now, sometimes it will seal that wound all the way back up, and it'll be buried. But if another fire comes through before it seals that wound up, it'll actually scar again, and it'll scar more easily. So trees that still have scars when the next fire moves through, and I have an example up here, will keep scarring every time a fire comes through. Sometimes there's other evidence of damage. This is a frost ring. It's cellular damage that's caused when you have significant cooling during the growing season. So it's called a frost ring. You had a growing season freeze that people are still trying to understand sort of physiologically if it's a collapse or an explosion or disintegration of cells. But either way, the cells are destroyed. In the case of this is a frost ring from whitebark pine in Wyoming that corresponds to a volcanic eruption that caused cooling event that affected the northern hemisphere. And this was a volcano that erupted in the subtropics and affected a tree growing at 10,000 feet in the greater Yellowstone. And I actually found that my frost rings lined up with significant volcanic eruptions. So not only do we see, well, it got really cold during the growing season that year because of a volcanic eruption. So, yeah, the question is about how you tell it's a frost ring. It takes some practice. We found them on my trip to Lake Tahoe, and students were seeing them for the first time. They caught on pretty quickly. It's this thing right here. So you do see this kind of jagged, ragged, sort of zigzaggy line across here. You see some resin that the tree's been damaged, so it's exerting something to that area. And I think it looks like the cells sort of implode. Yes?
Have you cored anything this summer, and does this past winter look like that in Kentucky?
No. So what happened in Kentucky, we had a pretty significant freeze. Everyone remembers over Christmas, probably, right? It wasn't during the growing season. This has to happen during the growing season. And the trees are particularly vulnerable for that reason. They're still transporting water, and it suddenly freezes. Now, when you can see maybe is if that freeze caused any dieback of your plant, to where it could reduce photosynthesis, maybe you'll see a reduction in growth over time. I lost a few plants in my yard to that freeze. Can't really, I don't know, they had come back every spring, but they didn't come back this spring.
Different than hardwood. Last winter, I've never seen, in my 60 years, I would say that is the worst winter I've ever seen. Looking at boxwoods, fake laurels.
Yeah, so it could cause...
I was just wondering if you noticed it in core, so that wouldn't show up in the core.
It might, but it won't show up as a frost ring. So it might show up as a change in growth rate over time. That would be my guess. Because now we did also get snow and a little bit of ice with that freeze, so if there was damage to the crown, potentially you'd see other things. So if it's a conifer, maybe you'd see what are called traumatic resin ducts, where it's transporting resin to injuries because of that. But it's not going to react until the following growing season. Now, you'd have to see a few years too. So it'd be a few years out from now to core the tree and see. Would be interesting if it was enough to have an impact. Yes? It varies by location and by species. So our growing season here is pretty long. You start when your trees are budding out in the spring till like September, October. My whitebark pines in Wyoming, sometimes in July they hadn't started growing yet or putting on ringwoods yet, like a month maybe 2 if they're lucky growing season, that's it. I was always amazed how quickly they could grow in a relatively short period of time. So some areas you have really short growing seasons, some you have long ones, and they could be getting longer. In the city, we see the influence of the urban heat island, changing phenology of plants in the city, they're budding out sooner, things like that. One research thing I'm trying to investigate is that affecting the trees?
Speaking on this problem, is this graph that we're seeing, is it the age of one tree or is it different? Because my question is, does it matter of the age of the tree? Like the young tree might be more vulnerable during the growth season compared to the older tree that I would think that maybe this tree is about 20 years old and it's
Yeah.
that problem?
Yes. Yeah. The question was about vulnerability of trees to certain things based on age. So yes, for some things, young trees are more vulnerable. Frost rings is an example. Young trees are more vulnerable to these. That usually goes to show that if you have a very old tree and it experiences a frost ring still, it's a very significant event. Some species are more vulnerable than others. White bark pine has a very thin bark, so it's more susceptible to frost ring than its neighboring species, spruce, which had pretty thick bark. So I saw more frost rings in the pine than I did in the spruce. I did see a lot of frost rings in young spruce, but then never again. So they were more vulnerable when they were young. They got less vulnerable over time. So there is that factor as well.
You may have mentioned it. What is the name of this tree that what's this tree?
This one?
Yeah, the one that we are talking about.
Oh, well, these are different. This is white bark pine.
Oh, okay.
Yes. So one interesting one that I found was Juana Patina in Peru in 1600. Caused a frost ring in my trees, but also all the bristlecone pines, the oldest trees on the planet, frost ring in that year as a result of that eruption. And then the last thing that I also investigate, especially here in Kentucky, is the impact of humans on trees, and specifically sort of how humans and land use change are reflected in tree ring patterns. We have a lot of examples of parks that I mentioned before that might have been old growth that was cleared for agriculture, pastoral land, for timber. Now that it's a park, it's reforested, and I find these trees that were there through all of that. And you see those changes in their growth over time. It's actually pretty cool. You're like, this tree was here in the 15 and 1600s. It survived land clearing and colonization, and now we're seeing it change again as the forest grows back in around it. So all of these things are affecting a tree. Yes.
You know about the tree, the older tree in Cave Hill?
I'm actually quarrying the trees in Cave Hill to work with them on the actual ages of their trees. So,
Gotta go see it.
I mean, I've been there. If you're talking about the ginkgo,
Well, it's the tree I was told had been there since the Civil War.
okay,
Before Cave Hill was Cave Hill, and it was a farm.
right. Yeah, it makes sense. Those, call them wolf trees, the lone wolf left behind, survived land clearing, and is still there now. It's actually cool. Yeah. So I go out, and you'll see this next week. I collect cores from the trees, I mount them. Actually, I turned the sound off because it's a little bit tricky. But you'll get to see this increment bore used next week. We put them in wooden core mounts because they're actually pretty tiny. They fit in a paper straw. They're like 4 or 5 millimeters, less than a pencil. So we actually have to put them in these mounts that I have in the examples here before we sand them. Because as you can see, I'm using a bench sander. I'm like holding it upside down. I'm not going to hold something that's 5 millimeters against sandpaper. I won't have the tips of my fingers or fingernails left, and probably not much of the core left either, trying to do it that way.
Your
It depends. Usually we're aiming for the middle because we're trying to get the growth, all of the growth we can of that tree. We usually take 2 cores per tree. And if it's a smaller tree, sometimes to cheat and get 2 cores, we just core one side out the other. Sometimes that involves collecting samples from trees that died a long time ago and are hidden in structures and artifacts. This is an example of some of the more extreme. I don't like to do crawl spaces. They just put this plastic down, so I was like, okay, I can do it. I'm scared of heights and spiders. Not 2 things to be afraid of if you're a dendrochronologist. So I've been actively fighting those fears. I'm not afraid of small spaces, so at least there's that. So kudos to my undergrads who crawled in there with me. Angel here was playing Eye of the Tiger on his phone as we were crawling in. We played music. It actually helped a lot to have a soundtrack while we were down there. We didn't feel so alone. This was under a home in Charlotte, North Carolina. So living trees aren't the only place that we get tree rings from. And in some places like Kentucky, where almost all of our old growth is gone, the only place you can find old tree rings is in buildings. Trees that were cut in the 1800s but started growing in the 1600s are hidden inside of these structures. Also hidden inside of these structures are the history of the people who lived here before the colonizers did and how they used the land. So that's a big part of what I've been doing in my lab, is looking at structures as ways that we can capture that hidden history. So these tree rings are hidden, but so is the history of how this land was managed before the settlers, the colonizers, got here. Sometimes it involves going out with a chainsaw and collecting sections from what we call remnant wood. Just like the long dead wood hidden in a cabin, this is long dead wood that's just laying on the landscape. I do this more often out west, where it's dry, and there's lots of conifers that are really resinous and resistant to weathering. Out here, if you go find a log in the woods, what's it usually like? Spongy, rotten, yeah. It's pretty wet around here. Things that fall over don't tend to stick around. In the case of my dissertation site, this is the Beartooth Mountains. I have to pinch myself every time I look at these pictures. I'm very, very lucky and privileged to get to do this. These trees that sometimes been dead for hundreds of years and still might have bark. I found bark from 1600. They stick around on that landscape for a long time.
Can you use petrified wood?
The question is, can you use petrified wood? Sometimes in petrified wood you can measure the tree rings, which is really cool. But a big part of what we do as tree ring scientists, we date tree ring patterns against other patterns. And there are no tree ring patterns from millennia ago, tens of thousands plus hundreds of thousands of years ago. So sometimes I haven't got to do it yet, but my colleagues will measure it and then sort of relatively place it in time based on what they know about the age of that petrified wood to get a little bit of an indication of what species were there, how they were growing, what the climate conditions might have been like, even if we can't actually date them to 1 year. Yeah.
If you have a tree that has fallen and you want to cut a cross section of it and date it, how high up from the base, like that roof layer, can you go and still have it be accurate? So you want to essentially make it.
Yeah, so the thing that you do lose, so a tree established, if you go out in your yard and your mulch, you find your little cedar or maple this big, you're not going to catch that little 1 inch off the ground when you go in with a borer or cut it. You lose all the years it took for a tree to get so high by cutting or coring that high. So to actually get at the age of the tree, you want to get as low as the tree as possible. If you have a dead tree, and yeah, it might be difficult to cut through all that stuff, but you're better off trying to cut through that stuff to get the true age. You'll find a lot of irregular growth from the roots and the buttressing and things, but you can still count and get an age. If you go further up, you're getting further and further away from the age. Now, the outer ring will be the same all the way down. So if you want to know when the tree died, you can get that from various places. But for its age, you have to go lower down. Yes?
When you find a dead tree, how do you know how long it's been dead? Are they dating or dead?
So the question is, how do we know how long a tree's been dead if we have a tree that is dead? We use the pattern of the tree. So this is how I date logs in a log cabin. It's the same way I date this tree here. It's been obviously dead for a while. Trees growing in a region will have a distinct pattern of wide and narrow rings that are reflective of the climate of that region. I think of it like a fingerprint of that area. So if you have a record, say, that's a few hundred years long for that area from living trees or whoever's done work before you, they have that pattern. You take a sample from a log in a cabin or from dead wood on the landscape, and it has its own pattern, maybe 100 years long. We take that pattern and we match it against the pattern for the region that's been developed before we got there, and it will fall into place. So let's just skip ahead a little bit. And also I know we're doing okay. We're getting close to question time. So this is just sort of an example. It's pretty simple, right? This is our pattern for the region that's already dated. It goes from 1792 to 2012. This is the pattern from our log in a cabin, our deadwood on the landscape. It has a pattern of wide and narrow rings. Actually, it's more like this is the fingerprint and this is the database, right? We run that fingerprint through the database until, bam, locks into place, right? And once it does, now we have a year for every ring in that, what we call it's floating in time. And especially we have that outer ring. Where did it go? Right here. That's the year the tree died. Now we do have to have bark or the tissue just under bark to say we know when the tree died. But you'd be surprised how many cabins and stuff around here still have those things on them. I've been in an attic looking at rafters and have found bark or outer edge. You just have to know where to look for it. Yeah.
So that, like, you don't have to have the whole process of the tree, you just need bark and wood and enough of the fingerprint.
Yes. Yes, you need bark and enough of a fingerprint to date it. Now, we don't just do this visually. Someone asked me that one time, and I thought, I should clarify. We do a lot more than just this, right? Because this could be a little bit subjective. We do this statistically, and so you do need a certain number of rings to have good statistical confidence that you've dated it correctly. The reason for that is, say you only have 15 years, and there's one narrow ring, it's going to try to match that narrow ring in like a million different places. You have to have a long enough span that you get a distinct pattern of narrow rings that can only fit in that spot. Then you know you've dated it. So yes, you got to get enough rings. Yes.
So in Stats 101, a sample size of 20 is usually taken. What is your sample size? 20, 25, 30?
So a number of cores, we often,
It's
like,
range,
or trees.
You know, how many?
60, preferably 100. Yes, preferably 100 or more is what I shoot for. At least on a few of my samples, right? Get that good, strong dating in place. And then maybe some of the 60-year-old ones will do well. But 60 is usually a firm cutoff for me. Below that, you get what we call spurious results. Like you just be dating it by random chance. It's just sliding into a place where it fits, just based on 1 or 2 years. So let's see. We're getting into what's called the principle of cross-dating. So just to sort of skip ahead a little bit, this is a really important foundational principle of what I do. So you can't just count the rings. Now, you might get away with it, especially if you're just sort of curious, what's the age of a tree? If you're curious and you're off by 1 or 2 years, no big deal, right? Especially if you're talking a few 100-year-old tree, maybe you're off by 1 or 2. If you're like me and you want to date when a fire happened or when there was a drought, you can't be off by 1 or 2 years. You have to know the absolute years for every ring. The way that we do that is called cross-dating. The simple way to explain it is pattern matching, which I've sort of already explained how we date remnant wood. We go out to a site and we core a bunch of trees. And we have to match the pattern in all the trees to all the other trees. Then we might date that site against an external site to, again, make sure that that pattern matches. To provide an example, because this is really the more technical side of what I do, we haven't really gotten there yet. I haven't warmed you up. Up here we have 2 cores. In example A. We go along and we look. We're like, okay, in 1892 there's a narrow ring. You pick up your next core. There it is again, 1892. That's good. The patterns are matching up. You grab another core, you're like, 1891. Something's wrong. Now, that something wrong could be you miscounted. Or it could be that something is different in that tree. So what happens is your pattern gets off. And you might notice that here in this example. Here, the pattern's on, but here, the pattern's off. 10 should be the one after these narrow ones, as it is down here. But up here, it's not. It's probably really hard to see my people in the front. Notice anything different about this tree and this tree?
3 really close together, and the other one's 4 really close together.
So I think it's 3 and 2, but yes, this one has 3. 1, 2, 3 narrow rings. That one only has 2. Because of that, as you were matching your patterns, the patterns slid off by 1. This is what's called a locally absent ring. What it means is that ring, the third ring that's here, is not present in that core from the other tree. Locally absent rings occur when conditions are so stressful that the tree does not put on an annual ring. Now, maybe it doesn't do that all the way around. The best way I've heard explain this is trees grow as a response to a growth hormone called auxin that actually comes from the top of the tree down, like melting wax. So imagine melting wax is coming down the tree. It doesn't come down perfectly evenly. In a good year, the tree produces enough growth hormone, it gets all the way from the crown to the roots, and you see a ring all the way around. In a stressed year, the wax comes down. Maybe it gets to this side of the tree where you cored, but it doesn't get to this side. Or maybe it doesn't get down at all and it's missing all the way around. So that tree didn't put on a ring that year. This is the only way we know how to find something that isn't there. Imagine your job is to find things that don't exist in all places. So we use this pattern matching to do that. And this is showing the notation system, so how we know. The other example's right here. There's a really narrow ring right here on this core, but it's missing from that one. So now the pattern is off by 2. Yeah.
I thought I understood what you're saying, but maybe I don't. Does growth always occur completely in a circumference around the tree, or is it possible to have a crescent growth?
and therefore your boring might be different depending on which angle you come into the tree.
Yes, I think I understand your question. So is the growth all the way circular around, or can it be crescent? So we call it like wedging or pinching, rings that pinch in and out. So a ring actually might like be gone and then appear and then be gone and then appear and then be gone. And so if you core through a spot where it isn't there, it's locally absent. Doesn't mean it's completely absent all the way around, but you missed it with your core. We take 2 cores from each tree to try to account for that. Hopefully you catch it on one side if you didn't on the other, because we usually start by dating a tree within itself, and then dating a tree to another tree, and then dating that tree to all the other trees, and then dating all those to another, so it builds, to make sure we know that we got everything correct. Yes?
The closer you get to the ground, the better, or not necessarily?
Not necessarily better in terms of absent rings. If you're after the age, again, you want to get low to the ground.
So rather than turning a handle with a cordless drill, you don't have the handle getting in your way.
Yes, so sometimes we have really long increment borers that come, 24-inch increment borer has a 24-inch handle. You can only get so close to the ground. But sometimes we put the 8-inch handle on the long borer. Now, imagine physics is not working in your favor when you're turning something like this. It's actually easier when you can do a long lever, yeah. So it's tough. And you're on your knees, and so that affects as well. Trees are really hard to core, and you have your whole body standing up, and you don't, low to the ground.
Well, what I was asking you is when a good cordless drill
The
is turning.
Yes. Folks are trying to figure that out. Now,
With slow speed with a lot of torque.
it depends on the species. Only for some species have the drills been able to go all the way in. The danger with the drill is that it likes to bog down. Your increment borer will bog down, and your drill will kick on you, and people will break their wrist. Yeah. So imagine, you're holding the drill, and it bogs down, and the whole drill whips, and you're holding it or holding a handle, either way. So they found it to be dangerous. Also, there's a lot you understand about how well things are going by feel and by sound. And you get rid of all of that when you drill, so the chances of getting a borer stuck and things like that go way up.
Technology is not on your side.
It's getting there. As a person who cores oak and hickory, I look forward to the day they find something that makes that a little easier. But I haven't tried some of the new tools yet because of the reasons that are out there. But I have colleagues who have been working on them with hardwoods. They usually find you might get in through the sort of softer sapwood, and then you have to manually do it the rest of the way. Or you might be able to back it out but not get it. Things like that. It just varies every time. Now, different types of drills do better with the kick and the bogging down and things like that. So the tool matters as well. And you have to have a lot of batteries and things like that. All the things you have to consider for field work. If anyone's done field work before, you probably know. So we're basically asking questions. We're getting close to 8 o'clock, so we are running out of time. We sort of, through questions, got through a lot of the principles. Can refresh them a little bit next week. So make sure if you're still puzzled over certain things, we'll get to talk about them some more because we kind of jumped the gun on a few things today. But I think that's great. That means many of you are already ready to start talking about actual applications of the science. I'll bring examples of tools next week, including the bit we use for historic timbers. We use the drill for that. And then the increment borer, and we'll go outside and core a tree. So I wanted to sort of introduce the plan. Oops. There we go. For next week and the next few weeks. Because I was kind of, well, I can't get there. My mouse is active. We'll be outside, so dress appropriately. If you want sunscreen, hats, things like that, bug spray, hopefully not necessary. But just note we'll be outside for part of the adventure next week. The goal is to talk about tools and applications. We'll introduce a lot of the things, and I'll show some pictures and give some case studies of the things y'all have asked about today. We'll talk about dendroarchaeology, tree rings and fire, and then some case studies and examples of how we use tree rings in Kentucky to understand our history, the human and environmental history in the state here. If you're curious, folks, you can stick around. I'll go through what I have up here. I have some archaeological cores from Kentucky, from white oak, white ash. So it's also one place we can still find a lot of old white ash wood as the ash are disappearing. And a piece of hemlock from Whitehall Mansion on Lexington Road. This hemlock actually came down the Ohio River from central Pennsylvania. A story we were able to put together using tree ring science. Pretty cool. I brought some living core examples after mounted. I brought some poplar and oak from Kentucky and some Doug fir and white bark pine from out west, just to sort of show you. This tree established in 1543. It took that many years for it to go from here to here. 1543. This poplar from Bernheim, 1917, from here to here. All right, so about the same distance, a big difference in number of years, mainly because of where they're growing, the conditions. This is a piece of a log from a log cabin. So sometimes I get lucky and maybe they remove some timbers for windows and things, and I could get a whole piece like this rather than a core. This is tulip poplar from a cabin in Estill County, Kentucky, not too far from Red River Gorge. I brought my oldest sample in terms of when it existed, not in number of rings, but when it existed. This tree, the inner ring on it is 707. This tree started growing over 1,200 years ago. This white bark pine from Greater Yellowstone. Yes. I have an example of, this is Engelmann spruce from the same area. This one's not as old. Painter's tape is not the best. It started growing in the 1600s, so it did take it that long to go from about here to here. So relative to around here, still slow. This is an example of one that has fire scars on it, if you're interested. It has multiple fire scars. And then I brought some little babies from Lake Tahoe to show reaction wood. These are the trees that get buried under snow every winter. And so they have that really uneven growth. They're also kind of cool because some of these that are like this big are like 50 years old. These are white firs. I have white fir, I think all white fir, yeah.
Have you been to the things from the coast, Windblow, Point Reyes in California, Jones Beach or Fire Island Pines in New York?
So yeah, I haven't worked on coastal trees other than the Florida Keys. So I worked with slash pine and fire history in the Florida Keys. But I guess I've been a lot of mountain, so I like to work at high elevations. A lot of them are really old, really stressed, really climate sensitive trees. And then also interior, I've been working in sort of Daniel Boone National Forest and places around here in Kentucky. So ask me questions if you want. I'm happy to linger a little longer. You can look at some samples, otherwise I know we need to wrap up.